now from here I'm going to discuss a very special kind of material. So it's called linear dielectrics. And so the property of this material is that the polarized polarized p vector is linear in terms of the E field. And so here you can see that there is a epsilon naught factor here, and this epsilon naught factor is simply to make this chi E, the electric susceptibility, a dimensionless quantity. So here in terms of unit, the chi E doesn't have any unit. The material is called linear dielectrics, but this actually means several things. So first, it means that there are no higher order terms. So what I mean is, in principle, the P could be proportional to the to the E, and also additional terms such as proportional to E square, and all these higher order terms are thrown away, and this means only the linear term is left over. And what's the second mean is that it's an isotropic, so no matter what kind of direction that you feed into about the E field, the final P field will also be in line with this E field, and this means it's not a tensor. So under these two assumptions, we call this kind of material that obey this equation as linear dielectrics. And for this kind of material, we can have some additional properties. So for example, the D field is simply by definition of epsilon naught E plus P field. And now, since the P field is also linear to E, we can also express in terms of E by using this formula here. And we can combine the two terms together, and it simply means epsilon naught times parenthesis 1 plus chi E. And this factor, all the factor in front, we can define that to be the permittivity of this material, and it's called an epsilon. And we also can define the relative permittivity, that is the ratio of the permittivity of the material with respect to the permittivity of the vacuum. So it's epsilon naught, and that is simply a 1 plus chi E, and this can be also called the dielectric constant. So in the homeworks, I express many things in terms of this dielectric constant. And as you can see, because the chi E, the susceptibility of the material is a constant, that is dimensionless, and this one is also dimensionless. Now let's look at an example. So for example, it's similar to what we just discussed about the wire. So except that this time we consider surface charge, a thick wire that carries a surface charge here. And the radius of the wire is A, and then there is a dielectric there is also a thick shell of dielectric material. And now let's find out the potential at the center with relative to the outside. So similar to the problem that we calculated before, we can still use the Gauss law. So we can apply a Gaussian surface that is also a shape of cylinder, and now so the del and integrate over this cylinder, the so the d dot a must be equal to the free charge that's enclosed, and the surface side of the cylinder, the d is perpendicular to this s direction, so the s is the s is along this radial direction, and the size of this surface is 2 pi times s times l. Now the surface charge enclosed is 2 pi times a times sigma times l. So if you compare, and the d vector should be sigma times a over s, and along the s direction. Of course, this is for s larger than a, because inside the wire it's a conductor. And now if we look at the electric field, let me see. The electric field is simply 1 over epsilon of d, because we just discussed above that the d should be proportional to the permittivity times d, and I simply invert this equation. And remember that here inside and outside the permittivity is slightly different. So when we are inside this material, it's actually permittivity is epsilon, and then times AOS s hat. So this is within the shell, and if it's outside the shell, the permittivity is epsilon naught, because it's in vacuum. So for this kind of linear materials, we can actually calculate the corresponding E field. So remember, in the beginning of this lecture, I said that for a generic material, the E field might not be known, but for this kind of linear material, we can actually find out what's the E field inside. Now, if we look at the potential, so the potential can typically be written as the negative of an integral of E dot dl, and where this integral typically goes from the infinity to your point of interest. Here we are looking at the infinity at the center, so it's up to 0. Now if we try to integrate this thing, we actually see that first we don't need to integrate up to 0. We only need to integrate up to a, because inside the a it's a conductor, so the conductor is an equipotential surface. And if we do this integral, then we have to split into 2 terms. So one is outside to B, another is from B to A. So now you can actually see that the first term is log B, and the problem is that if you subtract the log of infinite, the log of infinite is actually infinite. So this problem is special. So you cannot actually use the infinity, the reference point, because the potential is log R, log S, and so we actually cannot use the boundary here as the as from infinity. Instead, one plausible place is to actually place the boundary at B, and in this case, this term is simply can be neglected. And then this means that we simply need to integrate the second term, which is 1 over epsilon log A minus over epsilon log B. So in the homework, you will be asked to calculate a similar problem, but you will be asked to calculate the case of a sphere. For sphere, you don't have this kind of log problems, and you can actually find the potential relative to infinity instead of different arbitrary point in this case. Now, here, if you look at our calculations of this entire problem, we actually don't need to care about what's exactly the induced charge. So, in this problem, we only know the free charge distribution, which is the sigma over here. And from the sigma alone, we can calculate the displacement vector d, and then from the displacement and combined with the permittivity epsilon, we can actually derive the E field, and from the electrical field we can again derive the scalar potential for this electrical field, and that already completes our problem. And we don't even need to worry about the polarization vector P. But in case you want to calculate the bound charge distributions, you still need to calculate the P vector. So for the P is epsilon naught chi E times E, because it's a linear material. So inside this material, and the P can also be calculated. Now, if you calculate the charge distribution, it's also simple. So for the bound charge, you simply need to use the divergence of this P vector. And remember that the divergence in the cylindrical coordinate is slightly different from the divergence in the spherical or in the Cartesian coordinate. And if you multiply, you have to multiply by this s and divide by s again. And you can actually see that if you multiply by s, this P is no longer s dependent, and so this volume bound charge is actually 0. And what's left over is the surface bound charge, which is P dot n. And so there are two surfaces. One is the outer surface as the edge of the rubber shell. outer shells, and then another is that's the inner shell. So you simply evaluate the p dot n at these two places. And so for the outer shell, you replace the s by b. And in the inner shell, if you replace the s by a, the term over here cancels. So it's only one term. Now we calculate many times that somehow del cross p seems to be happen to be zero in this linear dielectrics. So is that always the case? And are there any exceptions? So remember that here P is strictly proportional to this E field, right? So then does it mean that because del cross E equals 0 everywhere, then does del cross P equals 0? Okay, so the answer is again no. So the reason is that indeed inside the material and outside the material, delta cross P is exactly 0. However, along the edge, the del cross P is might not be 0. So say here, if you look at the figure here, so if you look at the boundary and separate out the vacuum and the dielectric material, so for the inside, because of maybe the E field, it can be polarized along this direction. And for the outside, because there is no material, so the P has to be 0. So if you integrate along this path, this del cross this P dot dl over this closed path is non-zero. So according to the Stokes theorem, the del cross P along the surface is also not zero. And if you check the other surfaces, that if you put the integral along the outer or in the vacuum or in the dielectric, that is still 0. So you can imagine that the del cross P is non-zero at the boundary. Now let's take one step forward and saying that say that if the space is entirely filled by this homogeneous linear dielectric, then in this case the del dot cross P has to be 0. So say that our space is filled of some kind of homogeneous material throughout the space entirely, like from origin to infinity. Then in this case, what we learned about the E field should be entirely carried over to the D field, because in this case for linear dielectric, the P is proportional to E, so del cross P must be 0 within the material. And so the second term is similar to the del cross E equal to 0. And we also have this Gauss law, the del dot D equals rho free, which is similar to del dot E equal to rho over epsilon naught. So this means that we can find out what's the D field by two steps. So we can calculate the E field as if there are no dielectric materials, and then the D field for that case should simply be epsilon naught times E vacuum. However, because there is this material that throughout all the space, then we can actually calculate the D field, calculate the E field according to this definition of our D field as proportional to the permittivity of the material times the E field, and then from that, because the D field is already is proportional to the vacuum, and then we can re-express the D field in terms of the D field of the vacuum. So if you compare the E field in a material and compare with the E field without the material, there is actually a constant of an epsilon relative difference. And here, what this means is that if you put a charge in vacuum, that gives you the ordinary E vacuum. However, if you put a charge inside a dielectric material, then the E field might be reduced, and the reduction is this epsilon r. So here, this is the expression for a point charge embedded in a dielectric material. Notice that we no longer have this 1 over epsilon naught, and it's replaced by this 1 over epsilon. And this is the epsilon is the permittivity of this material. So you can actually see that a point charge will have a reduced E field, and the reason for this reduced E field is because you can think that here, if you put a point charge as the center inside a material, and the material will be polarized by this point charge, and the material there will be a negative charge being attracted to this point charge, and the plus charge will be slightly go away from the point charge, and this induced charge actually introduce an effect of shielding, but it's not exactly like a conductor. So for a conductor, you can imagine that there will be free charges building on the edge of the conductor until the E field inside the conductor is 0. However, in this case, our E field is only slightly reduce the field within the vacuum, and it will not 100% kill off the E field. So you can think of the dielectric material as some a similar effect to this some inferior metal, if you want, in this case. Now let's try to give an example. So remember that initially we calculate the capacity of a parallel plate capacitor, and so in this problem, so we can specify the charge Q above and Q below, and then use Gauss' law. We can find out the E field, and then from the from the E field, we can actually again by doing an integral of dl, we can find out the V difference. The capacity is simply is that Q over V or V over Q? Any of you remember if it's Q over V or V over Q? So now this time, let's see that what if we place a material inside of inside between this two parallel plate capacitor. So then there will be a material have a dielectric constant of epsilon r. So the E field will be reduced to this 1 over r epsilon. And then because the V difference is also reduced to 1 over epsilon r times B original. Say that this is that vacuum. Then the capacity will also pick up a factor of epsilon r times vacuum. So the common sense tells us that a capacitor should be increased if you put material inside. So it has to be capacity should be the definition of Q over V. So in this example, you see that stuffing some materials inside a capacitor simply going to increase its capacitance. So in fact, that is the general practice in producing the capacitors. So there can be some liquid materials or some solid material, but always there must be some materials in between your parallel plate and capacitor. So otherwise, the vacuum permittivity is too low. So the vacuum permittivity is the relative permittivity of air is very close to the vacuum, and even you have to have some specially designed material, and if you find the correct material, you can increase your capacitance by a factor of 100 or even more. Okay, so we discussed the boundary value, boundary conditions with the before about the with the D fields. So this was something that we just derived earlier. So now what we want to see if what this means for this linear dielectric material. So for linear dielectric materials, the P vector can be should be proportional to the E field, and the E field is again proportional to the D field. So we can re-express the P in terms of D, and now you actually see that here there will be a proportionality between the bound electric charge and the free charge. So this means that say you are given a problem without any free charge. Uh, then in this problem, there won't be any induced bound charge because the bound charge is actually directly proportional to the free charge. And now if you keep that in mind and say that in a we look for a region where there are no free charge at all, then this region there is guaranteed that the bound charge is also zero, and this is similar to our ordinary expression of a Laplace equation, where there can be a surface charge near some boundaries, but inside the system there are no charge, and we can use our technique of the Laplace equation to solve this kind of problem. So as long as you don't put any free charge in the region of interest, then you can use the techniques from the chapter 3 to solve for boundary value problems with materials added. Now, in terms of the boundary conditions, we discussed the boundary conditions here, and so we can also going back from the D field to the E field. So that is simply related by this permittivity factor. So D is proportional to the permittivity epsilon times the E field, and so this is simply a replacement. And now we also observe that the E field is we can write a scalar potential for the E field, and the E field, if you rewrite that similar in terms of the derivatives of the B, we get a similar expression comparing to the discontinuity equation in the scalar field. But here the difference is that it's no longer epsilon naught on the left hand side, and the total charge is replaced by the free charge on the right hand side. So just to remind you, so this is the what I write on the right hand side is the boundary value condition for the scalar potential near the boundary. And in terms of the potential itself, it has to be continuous. So again, we still have this same old boundary conditions here. So remember that we use the boundary conditions of the scalar potential to help us solve the problem of a sphere, of a charged sphere, I guess. So we will also look at this kind of problems here. So today we'll look at this last example. So the example is putting putting a dielectric sphere inside otherwise uniform potential uniform electric field E. So we've seen this kind of problem before, and so a similar problem is putting a conductor inside of this otherwise uniform electric field E naught. So just as what I mentioned here in the beginning of the lecture. So we can use the same techniques. So if you still remember, when we solve this problem, we try to analyze the boundary conditions first. So so the boundary conditions, if you still remember, outside should be so because the E field is partial V, partial the E field is gradient of the V, and to produce E field that's along the Z-axis, it must be the V must be minus epsilon naught Z, and in spherical coordinate is the Z is simply R cosine theta. So this is for R at infinity, and also we have the condition that at so right now for the outside we also have the condition at the R equals R. So at this boundary, the inside and the outside potential should be exactly equal. And then there is also another boundary condition that I just mentioned. Is the derivative of the derivative difference of the two. However, remember that this is a dielectric material, so be careful when you write out the boundary conditions. So inside there is an epsilon, so you have to use this. And so it's rho proportional to rho free. Sorry, it's negative rho free. But rho free here in our case is 0 because we didn't put any free charge on the surface. Now, if you still remember about the general solutions of this system with spherical symmetry, with azimuthal symmetry in spherical coordinate, then it should be a sum over all the angular momentums. So AL times R to the L plus BL over R to the L plus 1. This is the radial solution. And the angular solution is simply the Legendre polynomial. So inside the sphere, again, as we just discussed earlier, that because it cannot diverge at the origin, so the BL should be all 0. And then outside, normally AL should be 0. However, in our problem, the AL can take the value of minus E naught because of this strange boundary condition that far away must be the V must be proportional to E naught times R cosine theta, and this R this cosine theta is the P1, um, and this R to the power of L equals 1 is correspond to the term over here. So last time we also calculate that the L must be minus E naught, and so here this is now what we need to do is then to plug in our solutions inside and outside, and then match the boundary conditions. So the first boundary condition is continuous at the boundary. So inside the potential, it should be AL times RL times PL cosine theta, and outside the potential is only has minus E naught for the A1, and the cosine theta, and then all the terms with BL. So the then this gives us the condition that for A1, okay, for L equals 1, there is a special case that's because the right hand side involves L equals 1, and for other L's, it's simply AL R times L equals BL over R times R to the power of L plus 1. So, and now if you look at the discontinuity of this slope of this B, then we take a partial derivative on both sides. So so this is the outside derivative, and this is the term involving the BL. It must equal to the derivative inside, which is also remember the prefactor that the permittivity is slightly different outside and inside. Now if you combine these two terms, these two boundary conditions, you can actually solve. Let me see. This means that if you simplify the above equation for different L, so again we have to write down one special condition for L equals 1, because there is additional terms for the outside solution in the L equals 1. But for other L's, it's simply a simpler version of the boundary conditions. Now you can solve. Let me see. So you simply combine the expressions in the brackets, and here, and here. So it's a little bit messy, but if you find out yourself, the answer is AL is 0 when L is not equal to 1, and AL equals A1 equal special equals epsilon plus twice of the epsilon naught, and then the BLs simply can be related to AL through the expression over here. So now if I look at the potential inside of this sphere, it's actually something very simple. So if you write in terms of z, then and if you take a derivative of this inside potential, take a gradient, and you can find out that the electric field inside this sphere is actually proportional to the original E field inside the sphere. So remember that the outside E original should be E naught along the direct direction. So here you can imagine that if the polarizability, here the relative permittivity or this dielectric constant equals to 1, then the inside should be exactly equal to the outside, right? So that's trivial, or that's expected, because the dielectric constant equals 1 means vacuum. So if you don't put any materials, then the inside E field should be the outside exactly the same as outside. And now we put some materials inside, and you see that that's simply going to scale down the electric field by a factor of 3 over dielectric constant plus 2. And there's also some, you can actually also calculate the potential out and the electric field out, but the expression is a bit long.